Imagine a particle that is its own antiparticle, a quantum entity so elusive that it has evaded direct detection for nearly a century. This isn't science fiction, it's the fascinating reality of Majorana Fermions, hypothetical particles first predicted in 1937 by Italian physicist Ettore Majorana. Unlike ordinary particles that have distinct antiparticles, such as electrons and positrons, Majorana Fermions challenge our understanding of matter, antimatter, and the very fabric of quantum mechanics. If they exist, they could not only revolutionize our understanding of fundamental physics but also unlock the potential for ultra-powerful topological quantum computers, machines capable of solving problems beyond the reach of classical computers. In this article, we'll dive deep into the nature of Majorana Fermions, their historical background, their implications for quantum computing, and the latest experimental efforts to uncover them. To grasp the significance of Majorana Fermions, we first need to understand a fundamental principle in physics: particles and antiparticles. According to Paul Dirac's equation, 1928, every particle has an associated antiparticle with the same mass but opposite charge. For instance, electron E- has associated antiparticle positron E+, proton P+ has associated antiparticle antiproton P-. When a particle meets its antiparticle, they annihilate into pure energy. However, Ettore Majorana proposed something radical. What if there existed a class of fermions that were their own antiparticles? These Majorana fermions would behave unlike any known fundamental particle. Mathematically, they emerge as solutions to a modified version of Dirac's equation, the Majorana equation, which describes neutral spin -1/2 particles that do not require distinct antiparticles. Majorana fermions would 1. Self-conjugate nature. A Majorana fermion is its own antiparticle, meaning that if it interacts with another of its kind, it could annihilate itself, but only under certain conditions. 2. Charge neutrality. Unlike electrons or protons, Majorana fermions must be electrically neutral, making them difficult to detect. 3. Exhibit non-abelian statistics. In certain quantum systems, they exhibit exotic non-abelian statistics, meaning their quantum states change in a way that defies conventional particle interactions. This is crucial for quantum computing applications. While Majorana fermions were first proposed as elementary particles, detecting them in free space has proven extremely difficult. However, physicists suspect that they might manifest in two main areas. 1. Neutrinos. Are they Majorana particles? Neutrinos are mysterious, nearly massless particles that barely interact with matter. Some physicists speculate that neutrinos could be Majorana fermions, meaning that a neutrino and an antineutrino are actually the same particle. This could be tested via a rare nuclear process called neutrinoless double beta decay, where two neutrons decay into two protons and emit two electrons, but no neutrinos. If observed, this would confirm that neutrinos are Majorana fermions, reshaping our understanding of particle physics and the imbalance of matter and antimatter in the universe. 2. Majorana quasiparticles in condensed matter physics. Even if fundamental Majorana fermions remain undetected, scientists have found possible quasiparticle analogues, collective excitations that behave like Majorana fermions, in condensed matter systems. These Majorana zero modes appear in special materials, such as topological superconductors, materials where electron pairs behave in ways that mimic Majorana physics. Quantum spin liquids, exotic states of matter where Majorana-like excitations emerge from complex magnetic interactions. Nanowires and semiconductor superconductor junctions, experimental setups that can host Majorana modes at their edges, which could be harnessed for quantum computing. One of the most exciting applications of Majorana fermions lies in topological quantum computing, an advanced form of quantum computation that could overcome the major challenges of traditional quantum computers. Unlike qubits in conventional quantum computers, which are fragile and prone to decoherence, losing information due to environmental noise, Majorana-based qubits are topologically protected. This means their quantum states are stored in a way that is immune to small disturbances. This property stems from their non-abelian statistics, which allow quantum information to be encoded in their braiding motions, twisting Majorana fermions around one another in a controlled way. This makes quantum computations more robust and less error-prone. Several tech giants, including Microsoft, have invested heavily in the search for Majorana-based quantum computing, believing it could pave the way for a scalable and practical quantum processor. Over the past decade, physicists have made significant strides in the search for Majorana fermions. Some key milestones include 1. 2012 nanowire experiment, Delft University of Technology, Netherlands. Scientists observed signatures of Majorana zero modes in indium antimonide, INSB, nanowires coupled to superconductors. 2. 2016 Microsoft's quantum research effort. Microsoft announced a large-scale initiative to harness Majorana Fermions for quantum computing, focusing on topological qubits. 3. 2018 IBM's skeptical review. Some studies challenged earlier experimental results, raising doubts about whether the observed signals were truly from Majorana particles. 4. 2020 more refined experiments. New experiments using ion-based superconductors and advanced nanowire designs provided stronger evidence for Majorana zero modes. While no conclusive proof has been found yet, the search continues with increasingly sophisticated techniques, including ultra-sensitive spectroscopy and advanced material engineering. Majorana fermions remain one of the most tantalizing mysteries in modern physics. If they are proven to exist as elementary particles, they could unlock profound insights into the nature of matter, antimatter, and fundamental forces. Even if they only exist as quasi-particles, they hold the key to revolutionizing quantum computing by making it vastly more reliable and scalable. As experimental efforts intensify, the next decade may bring the long-awaited breakthrough that finally confirms the reality of Majorana fermions. Whether in the depths of particle physics or the cutting edge of quantum technology, these enigmatic particles could redefine the boundaries of science and computation. Will we soon uncover their secrets? Only time, and more groundbreaking experiments, will tell.